Okay, it's 9 o'clock. So, good morning, everyone. Trust everybody had a good evening, and is eager to listen to the fourth lecture of Dr. Crosby this morning. And as you know from the previous lectures, today it won't be any more about theory. It will be about the practice of using computational fluid dynamics codes. Yeah, some commercial, some open source, and Charles will guide us through them this morning. So, Charles, it's your show.
Thank you, Francisco, and good morning.
Yeah. So
good.
You're welcome to share your screen and start. And I'm sure in the next couple of minutes, more students will join us.
Thank you, Francisco. Good morning, everyone, and welcome back to this fourth lecture on CFD. As I mentioned last week, the way we'll do this week is to do 2 sessions of practical demonstrations where I'll walk you through some of the easier parts of using CFD programs. So we'll work with the commercial software today, specifically from 2 vendors. There are many vendors of CFD software in the market today, but the 2 biggest ones, certainly in South Africa, are Ansys with their suite of engineering analysis software, and then Siemens SimCenter. In this case, we're looking at Star CCM Plus. These programs are all used at the CHPC. People run very large jobs at the CHPC using 100 nodes, or in certain cases even more, so 2,400 parallel cores to run big models. The software scales extremely well. The more processes you throw at it, the faster it gets up to a point, but especially if your model is very large. When you're using it on an HPC infrastructure, you tend to not use the interfaces we'll see today. You tend to use command line batch files. All of these programs are highly scriptable and configurable, and they're actually quite easy to use in parallel, but you've got to set them up first. And when you start to learn these programs, obviously you work with the professional interfaces. These lectures are not intended for people who are already practicing CFD. If you've already been exposed to CFD and you've already worked with CFD, then you're going to get very little from these lectures. This is basics of introduction to using these commercial products. And if you're very familiar with them, I won't feel offended if you tune out right now, because I think we may be going far too slow for you. I'm not going to delve into the more sophisticated capabilities of the software. It's actually quite awesome what capabilities these software products have. But for the purposes of this demo, we'll just scratch the surface and deal with the simplest ones. So there's a series of videos, and we'll start off with a demonstration of Isom Cfd, which is a general purpose mesh generation package. It is available on the cluster because it is part of the Ansys suite of software, but it's intended obviously to be used interactively, but it's also got tremendous capabilities to be used in a batch mode. More on that later if necessary. I'll be doing the demos on the basis of pre-recordings. Experience has taught me that you never, ever do software demonstrations live. Everything will go wrong if you try to do that. So I've got a series of pre-recorded videos which have been uploaded on the Moodle, except for the Isom Cfd video, which is too large at this stage. We're trying to make a better plan with that. So with this being pre-recorded videos, perhaps it doesn't make so much sense to try to interrupt the session to ask questions. If you've got questions, we'll do it after each video. So there's a video on Isom Cfd, and then there's a video on Ansys Fluent, and then there's a series of short videos on using Star CCM Plus. So at the end of each little video, I'll give you the opportunity to ask questions. So let's start with this particular one. And Andrew, of course, you'll let me know if there's any kind of issue with the sound not working, or the video not even working.
Ansys is one of the largest suppliers of engineering and simulation software in the world. They have a very comprehensive suite of CFD software, and they have several meshing tools which they have either developed or acquired over the years. One of the most versatile tools is Isom Cfd, and I'm going to demonstrate how to mesh a simple problem with Isom Cfd. We start off with the model in CAD. Isom has quite sophisticated geometry generation and editing capabilities, but it's not very parametric. By doing it in CAD, we have the advantage of being able to develop our geometry in a parametric way so that we can change it quite easily. So this is our problem case. It is a semi-cylindrical obstruction in a square cross-section channel. I've broken the model up so that the individual surfaces have all got different names. It's quite useful to do this because once this model arrives in the meshing software and ultimately in the CFD analysis software, it's already identified and it's much easier to assign a boundary condition to each surface. You could keep it all together without a separate name for each surface, but then you have to separate them out in the meshing software. Not a big problem, but it's quite useful to do this at the upstream end. So if you make changes at this end, it's fairly easy to propagate this further through the process. So in this case, I've developed the model in a CAD package called SpaceClaim. SpaceClaim is also now part of the Ansys suite of software. So it's very easy to import a SpaceClaim model into Isom Cfd, where it arrives looking like this. So I've made very small changes to it in Isom so far, but this is basically how it looks. It's not so obvious because we switched off the shading of the surfaces, but when we switch on the shading of the surfaces, we can see how they've all been broken up into separate bodies or families to which we're going to associate boundary conditions later. You can see, for example, there's a bump and a floor and an inlet. So we take it back to a wireframe display. We've got different ways of meshing this. I'm going to demonstrate two of them. One is to make use of multi-block structured meshing, and the other one will make use of unstructured tetrahedral meshing. We're starting off with exactly the same geometric model. The geometry is represented as a sequence of points, lines, and surfaces. Because it's a solid model, there's effectively a solid volume contained between these surfaces, but Isom Hexa is not particularly concerned about that. So to create a Hexa model, we first of all have to create a blocking structure. Remember, we talk about it as a multi-block structured mesh. So you have to create the blocking structure first. We'll call the block fluid. Fluid, the default name is solid, but we shall call it fluid. We're going to encompass all our geometry, and we're asking it to project surfaces and orient with geometry. We select all the geometry. And it's created a block, a single mesh block for us. We can switch off the geometrical representation so we can see what the mesh block looks like. It's very simple at this stage. There's nothing to it. It's a purely prismatic block. We can already choose. There's always some nasty error messages in the software. Best just to continue, dismiss everything we've seen up to this point. We can now assign grid spacing on each edge. Because it's a block, those edge spacings get transferred to all the parallel edges. We'll see what that means in a minute. We've now got edge spacing. Create a mesh for this geometry. It's going to be a dreadful mesh because it's got no way really of accommodating this bump, but we'll do it anyway. Isom is a very intelligent program when it does the Hexa meshing because it's smart enough to recognize when a mesh face corresponds with a surface, and it'll assign that surface or that mesh face to that surface. And we can see what it looks like. Switch off the surfaces for a moment by switching on the so-called pre-mesh. So it's now already decided it can make a mesh, and it's not only made a mesh, it's made a mess. So it's not entirely dreadful. You can see how the mesh spacing has been transferred to all the parallel edges, which is very convenient. And it's even made some attempt at capturing this this bump. It's not great though. That's not a valid mesh. If you put that into a CFD solver, it will dismally fail. So we have to improve on this a lot. So we can do this by let's get our geometry back up again. There we go. There's our geometry. So we can do this by modifying our blocking structure, and we do this by splitting the block into multiple blocks. So we can take this edge, for example, and we can split the thing into 2 horizontal blocks. That's not going to help very much. What we're trying to do is to isolate this obstruction. So we make a series of splits around our obstruction. So now we've got our obstruction more or less isolated. That still doesn't help us assign a rectangular block to a half cylindrical body, but we can do that. But we can do that by so we can select certain mesh faces which will have the split in them. It takes a long time to figure out how to do this. Don't worry about it too much. The bottom line is that you want this. So it's taken that kind of rectangular block and it's split it up into 5 different blocks. And now we've got something we can work with. It's not immediately that useful because trying to project a rectangular face onto a cylindrical or a circular surface produces very poor mesh quality. So we've got to tweak this a little bit further, and we do this by moving the individual vertices of the mesh. I've cheated a little bit. I've made like a cook in a TV cooking program. So I've done the tedious bits while you weren't watching. So I've moved the vertices so that they're inside that cylindrical object. And then comes one of Isom Cfd's tricks, which is to remove the blocks that we're not going to need. Before we do that though, let's do a further split of the mesh. And this time we'll split on an edge. Which will take that edge and split it nicely on the circumference of the cylindrical object. So having done that, we've got a better chance of getting this block represented as a decent mesh quality. We can now remove the bits of mesh block that we don't want, and we do this with a rather indirect approach. The indirect approach that we use is to move the blocks that we're not interested in to the so-called VORFN family of blocks. So we can zoom in here. We can take the blocks that we don't want, which is these ones, and we get rid of them. So this way we've now got a cavity in the mesh which is representative of a real life cavity. All that we now need to do is to move these vertices onto the corners and to associate these edges with these surfaces. I'll do that like you do in a TV program. So I've saved you the tedium of watching me move vertices in the mesh around. We can now switch on our pre-mesh and take a look at what we've got. Right, this is starting to look a lot more like a mesh. Let's switch off the geometry and shade the surfaces. And we can immediately see that we've got something that looks a lot more like a mesh, but the spacing is rather horrible. Where we've split the mesh, it has not always given us enough mesh divisions, but that's very easy to fix. Let's just switch back to wireframe spacing. Let's say we put 5 mesh divisions along there. That should solve most of what we're dealing with. Let's dismiss this and recalculate the pre-mesh. Yep, that's looking quite a bit better already, but we still need to put some more divisions along here. So let's do that. Let's use 5 here as well. Amazingly, this program recovers quite well from those error messages. There we go. Now we've got something that looks a lot like a mesh. And you can see the way that the bits of mesh map through into the various parts of the flow domain. We've captured the semi-cylindrical obstruction very nicely now. We've got some fairly decent orthogonal meshing going on there. Decent orthogonal meshing around the outside here. In real life, you would make the mesh spacing much finer like this, especially perpendicular to these wall surfaces. You would want a mesh spacing that's much finer so that you can capture the boundary layer. We're not going to do that. It's easy to do, but it's tedious, and I'm just trying to illustrate principles to you here. So that's what a multi-block structured mesh looks like. Depending on the solver that you're going to be using this, you could export this either as a structured IJK type of mesh or as an unstructured mesh, which is what most solvers can deal with effectively these days. In either event, you've got a lot of control over the mesh spacing, and you've got a lot of efficiency, and you can match your grid spacing very nicely to the topology of the object that we're meshing. We've noticed, for example, that if you were to calculate a CFD solution for a simple three-dimensional wing, if you use a block structured hexahedral mesh like this, you can get wonderfully accurate results with only about 120,000 grid cells. That's very little. You can easily solve that on a laptop computer, and the answers will be very, very close to any kind of theoretical experimental value. If you're going to try and do the same thing with an unstructured mesh, which cannot take advantage of topology, and I'll demonstrate unstructured meshes now for the rest of this video, then you would probably need well over 1 million cells to capture the same accuracy. So there's a lot to be said for structured meshing, but it is very tedious. It needs a lot of expertise to do it well, and it is becoming less and less common. There are certain applications such as turbo machinery where it's still very well used, and then you often have very specialized software to make the generation of such meshes more convenient. Now I'm taking the same model, exactly the same model, but I've removed the hexahedral structured blocking, and I've converted this to an unstructured model. The only thing that needs to change to make this an unstructured model is to tell the meshing program that there's a point inside this body, which we are calling fluid. That way the mesher knows what's inside and what's outside. You can do more than one body at the same time, and then you can give them different names, and the mesher will know to generate cells belonging to two different families, so that the solver will ultimately be able to distinguish, for example, between the outer fluid and the inner solid body, which may be useful if you're doing heat transfer. When you're doing unstructured meshing like this, it's really important to make sure that your model is watertight. The structured meshing is less concerned about that. It will tend to skip over small bumps or holes in the model. But an unstructured mesh will very often leak. It will leak grid cells through a region where there are, for example, holes, or where there, even worse, where there are overlaps. So we've got tools to help us fix the geometry, or at least inspect the geometry to see if it's valid. And we can do it by running this tool. Nearly all the meshing programs have got something similar. So this is the one that gets used in Isom Cfd, and when it's happy with what it's seeing, it will give you all red edges. By definition, for an unstructured mesh, an edge forms a boundary between exactly two faces. Think about this for a moment. If there was only one face adjacent to an edge, it would be open. If there were 3 faces coming together at a single edge, that would leave you with a 0 thickness surface. There are certain times when you may want to mesh something with a 0 thickness, but you've got to be very careful with that. Those things are called baffles. In this case, because I've created the model myself for CFD analysis, I've made very, very sure that it is watertight. So at first pass, all the edges come up red, which is exactly what we wanted to see. So we can dismiss that and move on to the actual meshing. So we've got a whole bunch of settings that we can use for the meshing here, such as, for example, the size, and it's most easily shown by this menu where we can give different mesh sizes for the different parts of the model, and we may choose to have a prism mesh for capturing a boundary layer, a viscous surface, or a viscous boundary layer, by setting up a number of prism layers. Don't worry too much about this. If you start working with this, you'll grasp it soon enough. So I'm just trying to show that this exists. So I'm quite happy with that lot. I've set this up previously, and we can now set this thing going. We're telling it we want a mixed tetra mesh. Uses the octave approach towards generating the mesh. There are others which may give you smoother meshes, and it should create the prism layer. So everything is set up, and we can tell it to go and do the work. It first creates a volume mesh, which it smooths before it starts working on generating the prism layers. Various tetra meshes do this differently. Others mesh the surfaces first and create smooth surfaces first, then extrude the prism layers from those surfaces, and then fill in the rest of the volume. This particular meshing algorithm works the other way around. It makes a full but very unsmooth volume tetra mesh first, then it smooths that, and then it creates the prism layers. So there are a couple of different approaches that can be used here. It's now finished with the generation of this mesh. Let's move to switch off the geometry and switch on the shading to see what we've got now. So now we've got a completely different mesh. So it's a tetrahedral mesh, triangles on the surface, and it's created these fine prism layers. So this is actually much closer to the kind of mesh that you would use because it's got the much finer prism spacing. We could easily have done that with the hexa mesh. In the interest of saving of time, I didn't actually go through that exercise. This is not a dreadful mesh. You would really like the transition between these prism layers and the volume mesh to be a little smoother than that. So you would probably, if you're trying to get a good solution, extrude a few more layers of prism mesh. Also, in the interest of actually capturing a decent solution, you might also set up a region of refined mesh downstream of this obstacle, because you are going to get some interesting flow characteristics happening there. I haven't done that simply because it's tedious, but it's pretty straightforward to do. You can define a region here, a block or a cylindrical shaped region, where there is a much smaller, larger mesh size. Of greater interest is that you want to export this mesh now to some kind of solver. So we can select Fluent as an as a software that we're generating a mesh for. Fluent is one of Ansys' CFD products. And then most crucially, we're setting up boundary conditions. You would typically create a fluid for the body of the mesh, and then for the surfaces, the one-sided surfaces, there's a whole bunch of them here. They're popping up under mixed unknown. The way it interprets varies a little bit with the characteristics of the model. So that one is the inlet boundary condition, and we can set that as a velocity inlet. The bump will be a wall boundary condition. You can choose how you're setting up this thing, but typically the floor would be wall boundary condition as well. Your outlet might be a pressure outlet boundary condition. The side could be a symmetry boundary condition, for example, and we could choose to set the symmetry plane also as a obviously symmetry boundary condition. And then the upper surface we could set as a wall again. It's not necessarily physically realistic. Let's just assign some kind of value for it, and then you can export it as a mesh file. So Isom goes away and does its thing, and most importantly, it writes it as a so-called .msh file. So Isom would have written a .msh file, and then we'll see what happens with Fluent if you pull a .msh file into it.
Righto, any questions at this stage? Okay, if nobody's got anything to ask, we'll move on to the next one, which is to have a look at what happens when we go into Fluent.
It is one of the most widely used programs in South African universities, along with Star CCM+. It is also very widely used. We have many users of Fluent on the CHPC system. You will recall from the mesh generation that I exported the model mesh, the mesh of the model, in a .msh format for Fluent. Now it turns out that .msh files are read by many different types of CFD software, but it's originally intended, of course, for Ansys Fluent. So I've already imported the model into Fluent, and it is shown here. We defined the boundary condition types in the mesh generator, so it already knows that the inlet is an inlet. It's showing velocity vectors going in there, and the outlet is an outlet, and these yellow surfaces are symmetry planes, and the gray surfaces are walls. So we can work through the menus on the left here to set parameters for this calculation. It's decided by default that the fluid that we will be using is air, which is a good choice. Then we can take a look at the boundary conditions. We maybe want to look at the inlet boundary condition. We can set the velocity normal to the boundary just as its magnitude, and let's set it to a velocity of 10 meters per second, 36 kilometers an hour. Okay, so let's go back to this one here, which is our models. We've kept most things off. We're keeping it simple. There's no multi-phase flow. There's no water, for example. We're dealing with air only. There's no energy equation, so it's an incompressible flow. We've selected the SST K omega turbulence model, which is a good compromise for many purposes. We're not doing any heat exchange. We're not doing any chemical species. We're keeping it nice and simple. Right, so we've got the models. We've got the inlet boundary condition, the outlet boundary condition. None of these we need to set at this stage. They're already correct. Then methods. This is important. There are many methods that we can apply here. So remember we spoke about the pressure velocity coupling method. So in this case you've got a choice of 4. The simple method, the simple consistent method, which is simply a variant of the same thing, and then PISO, which is an unsteady transient version of the simple family of methods. And then there's the coupled solver that we spoke about previously. We'll stick with a simple solution for now. You can use various schemes for evaluating the gradient terms in the equation. So the least squares cell-based method selected here. Pressure is second order central differencing. And then the momentum equations, you can select here between first order upwind, second order upwind, and then higher order schemes. We're going to start off with second order upwind schemes, and I think you'll find that the method doesn't converge very well. There's a good reason why it won't converge, but we'll discuss that while it's running. And then turbulence, we're using second order upwind terms for the turbulence equations as well. Controls. With the controls, we can set under relaxation factors to try and stabilize the equations. By bringing down these values, we slow down the convergence, but we also improve the chances of the solution being stable. If you were to use the coupled solver, you would have different parameters that you would be setting here. For reports, it's always useful to take a look at how your solution is progressing. And one of the most useful things is to evaluate a drag force on the bump. As your solution approaches convergence, so the drag force on this bump here should become constant. We want to monitor the solution as it progresses, so we will use reports. We'll look at the residuals of the equations. In other words, just how close are we coming to satisfying the integral form of the differential equations. And then we can also take a look at our plots, and in this case we'll be plotting the drag force. There's a bunch of other things we can set on, for example, auto-saving every so many iterations. We're not going to bother with doing that here. We're just going to go straight to running the calculation, and let's run it for 100 iterations to see how it gets on. Yep, we want to initialize the calculation. It's initialized it, and away it goes. So you can see how the drag force changes with iteration, and there are the residuals of our equations. So we've done 100 iterations, and it's nowhere near convergence. One of the reasons for this is that a solution like this will almost inevitably produce a region of recirculating flow in its wake, and that recirculating flow will be unsteady. So it's unreasonable to expect a inherently transient phenomenon like this to converge very well in a steady state solution. In order to get a better idea of what's happening with our solution, we can take a look at a contour map of the velocity on the bump and the sim plane. Now obviously on the bump it will be 0 for 0 velocity at the wall, but we'd like to see what's happening on our symmetry plane. So we can do that, and you can see here that we've got a fairly mixed up looking flow. There are many more things that you can take a look at. You can make a plane through this and put some velocity vectors on that, but as you'd expect to see, this is not making a particularly nice looking steady flow field because it's not a steady flow situation. One of the things we can do to stabilize the calculation to get it closer to convergence is to change it to first order upwind differencing. Let's go and run another 100 iterations. So we've now gone to first order upwind differencing. Now we'd expect the first order upwind differencing to be less able to capture the structures of the separated flow. It'll tend to diffuse or smear out the solution, and as a consequence it'll likely produce a better convergence. That doesn't necessarily make it a more or less useful answer, but it converges much faster. And you can see this here by the residuals coming down. So these residuals are a measure of how close we are to satisfying the equations. You typically want these to come down around 3 to 4 orders of magnitude. We can take a look after the second 100 iterations at our contours of velocity magnitude. Well, they're not looking bad. It's looking a lot smoother, which is what you'd expect to see with the residuals coming down like that. Let's run another 100 iterations. So convergence is progressing very well. If we take a look at our force, that's leveled off nicely as well. Once you start zooming in on this force, you'll find it's still oscillating, but the amplitude of the oscillation is quite small. So that's all looking very nice, bearing in mind that we're trying to solve something which is inherently not really physical. So we've got a nice smooth looking solution now, or reasonably smooth looking solution now. If we wanted to resolve what is really happening here, we'd use a transient method. So let's see what happens if we go back to our methods and we switch to second order upwind differencing of the turbulence of the momentum terms. It's a good question whether you should really go second order upwind on the turbulence. Most people I've spoken to tend to agree that there's not much point in that because the turbulence equations are so approximate anyway. So, right, so let's do another 100 iterations. Take a look at the residuals. As you can see, the moment we set it to second order, the residuals have jumped right up again, and they're going to continue oscillating like that. They're not going to come down much more than that. But what you will see when we get to the end of this 100 iterations, you'll see that the flow field is starting to look a lot more complicated. As you can see, the force has now become oscillating, started oscillating, and that is physically realistic. The force will be oscillating. So there you go. You can see it has now become somewhat more complex as it picks up more of the unsteady flow characteristics. So let's change the model now to a transient model. So having changed to a transient model, we should look at different methods, and in this case we'll be using the PISO scheme, which makes provision for an unsteady transient formulation here. Go to the running the calculation. So we'll use a fixed time step, number of time steps. Well, let's run it for 50 time steps, and the time step size that we will use is 0.025 seconds, and let's use 5 iterations per time step. So now you'll be doing a solution at each time step and then advancing from there. So as you can see, your residuals now change. They come down for 10 iterations per time step and then go up again. And this is not looking good. This is looking very bad. In fact, this is every evidence of a solution that's diverging, and it's diverging very rapidly. Stop at the end of this time step. There's not much point in progressing further with that. That would be a good example of trying to run transient with a time step that is too large. You can go and calculate what the appropriate time step should be, but we can just bring it down a little bit and work from there. In fact, there's every indication that the continuity equation is diverging. So this is typically what happens with a CFD calculation if you try to do something which is non-physical. And there we go, it's blown up on us. So see, this is not the correct way of approaching it. The more correct way of approaching it is to use an adaptive time step and to use a cell CFL number, Courant Friedrich Louis number, which is essentially a way of basically saying how many grid cells do we advance per iteration. So we'll reset the calculation and we'll do it properly. In other words, we're not going to guess the time step. We're going to use adaptive time stepping based on the CFL number, and we're targeting a CFL number of 1, which is generally a good approach to getting stability. We're starting with an initial time step of 1 millionth of a second. The first time step it will use a constant time step, and from then onwards it will adapt it. I have already reinitialized the calculation, so we can start from here. So we're starting from afresh. So you'll see every 10 iterations the residuals will take a jump as we advance in time. So it's now taking less than 10 time steps per 10 iterations per time step, because it's reaching convergence on a time step earlier than 10 iterations, which is a good way of accelerating the calculation. Our forces are only now starting to be generated because we're plotting the forces against time rather than iteration. It's rather an illustration of just how much more demanding transient calculations are than steady-state calculations. Reality is transient, but it may result in calculations that take so long to run that it's not practical. So we'll let this one run for a bit. We've now finished this phase of the calculation, but as you can see, the flow time has not advanced very much, and that is a typical problem with transient calculations. You only do transient calculations when you hope to learn something from that. So it's still in the early phases of developing a solution, but if we leave this to carry on time stepping, it will develop a flow field behind this obstacle with all sorts of interesting structures in it to illustrate the recirculation, separation, and vortex shedding. This is a very simple, it's been a very simple demonstration of how to use Fluent. The program has got many more physical capabilities, including heat transfer, radiation, chemical reactions, and a whole lot besides. It's an extremely powerful program. And there's a reason why it's very widely used in industry and academia. Ansys is one of the large
So at this point, anybody want to ask anything? Are you all still awake? Okay, so Solomon, as usual, is awake, for which I'm very grateful. So for your sake, I shall continue. Let's just share again.
Siemens Star CCM Plus is the second of the CFD codes very widely used at South African universities. It's also been used very productively at the CHPC. It does more or less the same things as Ansys Fluent, but it's got a different philosophy towards the design of especially the interface. So I'm going to walk you through an example of importing the same geometry as we used with the other case, and setting up a mesh and running a solution for it. In this software, we can use a single interface for setting up the mesh and for running the solver. So we start by importing a surface mesh. Now this time we're not using the space claim file, we're using an IGES file. An IGES file is a kind of a universal interface file between CAD formats. So it takes a moment to import. Once it's imported, it pops up in the display and we can see the very familiar geometry that we had before. We've imported it as a region. So it's a region consisting of a body and some boundaries. At this stage it's showing up as a single boundary, so we'd like to split up that boundary into a number of separate boundaries. So that's happened now, and once it's done that, we can assign names to each individual boundary. So these two parts form the bump. That would be the symmetry plane. So let's just call it symmetry, and so on. Right, so we've got our boundaries now split into different names. They're all showing up as the same type of boundary, which is a wall boundary. That's not particularly useful because not all our boundaries are wall boundaries. We'll keep everything walls except the inlet, which now becomes a velocity inlet, the outlet, which will make a pressure outlet, and the symmetry, which is of course a symmetry boundary condition. In order to run a CFD simulation of this geometry, we first of all need to create a mesh. So we've got a mesh continuum, and we can select appropriate meshing models. A surface mesher takes our initial surface tessellation and turns it into a higher quality surface mesh. We'll look at that in a moment. And then we'll use a so-called trim mesher, which is actually a cut cell Cartesian mesh, and we'll also have a prism mesh. In order to see what the mesh looks like, at this stage we only have a surface mesh. We'll open up a new mesh scene. And here we can see how our smoothly interpolated IGES surface has been turned into a tessellated surface. In other words, it's replaced all the NURB surfaces with surfaces consisting of triangles. And as you can see, you've got some very high aspect ratio triangles here. This makes the in-memory representation of these surfaces quite compact, but it's not an ideal surface for building a mesh on. So in order to fix that, we'll do a surface remesh. That's why we set the surface remeshing. In order to do the meshing, we need to set some parameters for it. As you can see from this list here, there's quite a lot of different parameters that we can set for the mesh. We'll start by setting a base size. Let's use 5 centimeters, 0.05 meters as the base size. Let's take a look at our number of prism layers. We'll use, as we did in the other example, 8 prism layers. And then we need to specify the thickness of the prism layer. In this case, we specify the entire thickness of the all the prism layers, not just the thickness of the first layer. So the value looks much higher. Right, those are pretty much all the parameters that we need to set, except now we need to make sure that our various boundaries are going to be shown as surfaces that need prisms attached to them. By default, all the boundaries will have prisms. So on the inlet boundary the outlet boundary and the symmetry boundary, we will customize the prism mesh by disabling it. We've set an overall target size of 5 centimeters for the mesh. However, the bump with its curvature could benefit from rather finer mesh, so we'll set a custom surface size for the surface mesh on the bump. So in this case, we'll set a percentage of base. Remember, our base size is 5 centimeters, so we'll set the minimum at 10% of that, so in other words 5 millimeters, and we'll set the target as 20% of the base size. So that will give us a much finer surface mesh on the bump. We're now ready to remesh the surfaces. So from the mesh menu, we can generate a surface mesh. That happens very quickly because it's a very simple model. And if we go to our mesh scene, we apply the representation no longer of the imported mesh, but of the remeshed surface. So you can immediately see it is still a triangular surface mesh, but it's of a much higher quality. It's very smooth, and it's isosceles triangles more or less everywhere. So this is a much better surface representation, so we'd be quite happy to attempt to generate a volume mesh based on the surface mesh, and that's what we'll do now. Generate the volume mesh, and away it goes. That finished very quickly. It's generated a mesh with a total of 93,430 cells. We're still seeing the surface representation here, so on our mesh scene we need to change this representation to the volume mesh, and that's what it looks like now. So remember, we've spoken about cut cell Cartesian meshing, and this is what we're seeing here. So this is actually quite a nice looking mesh. It's got the prism layers nicely resolved. It's got the surface of the cylinder quite nicely resolved, and it's captured all the edges quite nicely. So this is not a perfect mesh by any manner of means, but it's certainly a usable mesh. Having now finished generating an acceptable mesh, we've got to set up the physics of the run. So we've got Continua and a Physics tab here, and under it models that we can select. So we select models from it here. We're going to do as before. We're going to use a steady state simulation. We're going to work with a gas only. We'll use, in this case, a coupled flow solver. We'll use a constant density gas, and we'll use a turbulence model, and we're selecting a K omega turbulence model. By default, it selects the SST K omega model, which we've discussed before as a good general purpose choice. We don't need any other models. We can work with this one. Right, so all we really need to do now is to specify some inflow boundary conditions. So we go to our inlet boundary, physics values, velocity magnitude. There's a lot of other things that you should really be setting, but in this case all we really need to set in order to get a solution is the inlet velocity. So it's worth taking a look at our physics models, where we've got our coupled flow solver, and we are using second order discretization for the convection terms. So remember what we did in Fluent, we could set first order and second order for better precision or more stability. We'll run the second order. And right, we would like to be able to take a look at our eventual solution. So we'll set up a scalar scene, a new scene, a scalar scene. On the scalar scene, we can have a number of displayers. So we'll take a look at our first scalar viewer. There's a bunch of settings here, but the parts that will show in the scalar will be the symmetry plane. Then we would like to set the velocity, magnitude of the velocity, as the scalar that we'll be using. We'd like to have another displayer in the same image, which will also be a scalar displayer, but this time we'll use it for the pressure on the cylindrical part. So once again, we'll have nice smooth shading, and the parts that we'll be selecting here will be the bump, and the scalar field will be the pressure. We'd like to be able to monitor convergence, so we'd like to set up a report of a force, new report, force, and we'll capture the drag on the bump. So that gives us a force. We can rename it and call it the drag. And we can do two things additionally with this. We can create a monitor and a plot from it, which means we'll get graphs of the drag. So we're just about ready to do the run. So we need to initialize the solution, and then we can hit the run button. And away it goes. There's a lot of parameters that you can set for the solution, but now we're just dealing with the simplest ones. Started off with a little bit of reversed flow at the outlet boundary condition, which is not necessarily a disaster. We can take a look at our drag. As we've seen before, the drag oscillates. In this software, we actually get the ability to view the solution as it develops, which is quite handy. So we can take a look at the values and we'll be able to see if a solution is starting to run away from us. So we're once again seeing the kind of thing that you don't really want to see in a solution, which is that the residuals are not really coming down, and in fact they're starting to go up. The drag is showing an oscillating force, so it's what we've seen before, trying to run what's essentially an unsteady flow situation with a steady approximation and second order differencing. So we can pause the simulation there. We can take a look at the properties of the coupled flow, and we can change to first order upwind differencing as we've done before. And once again, you'll almost certainly see a much stabilized calculation with the residuals coming down very nicely, and you can see an immediate difference in the answers when we went from first order differencing, from second order differencing to first order differencing. So you never really want to use first order differencing for answers. It is not as accurate. It's stabilizing quite nicely, but at a different value. Residuals are coming down very nicely. The image, as we saw with Fluent, we get a nice smooth simulation which is not actually physically realistic. To capture the more complicated features of this flow, of course you do need to run it with a transient flow simulation, and you should really be running it with detached eddy simulation if you really want to see what's going on, but that'll take much longer. So as before, we're getting fairly nice convergence with first order differencing with a somewhat unphysical solution. As an experiment, we've now switched to a transient simulation, but this time we are going to be using the K omega detached eddy simulation model. So it's a lot more sophisticated on the physics that it's modeling, and it's going to be much slower. We're starting from a fairly good solution that we already had. We're using appropriate discretization scheme, and let's start running. So now it is running transient, so you'll see a change in the shape of the residual curve. We're using an implicit discretization in time, so we can use a fairly large time step, and we're running 5 iterations per time step. Our forces are not changing drastically yet, and our scalar scene is already starting to show quite a lot more features than the smeared out steady state solution. I will pause the recording here because it's going to take a while to get somewhere. When you're doing transient simulations, especially something as demanding as detached eddy simulation, you would really like to run it on a high performance computing cluster, and this is running on a fairly old desktop computer. So it's not ideal hardware for this illustration, but nevertheless it's the easiest way of getting a good recording of it. I've modified the scalar scenes a little bit to make it easier to interpret. We're now plotting 3 different variables. We're plotting a skin friction coefficient on the floor, plotting the magnitude of the velocity vector on the symmetry plane, and on the cylinder we're plotting the pressure, but we're using different pressure maps so that they don't get confused with each other. And see how the drag force is developing. You can see how residuals are developing. This is the kind of simulation that needs to run for a long time. We'd like to get to approximately 1 second to maybe half a second to 1 second of total run time before we'll get a steady state or a oscillatory solution that will stay more or less within the same bounds. I've now created an extra part in the scalar display, which is this cutting plane here. So it's giving us the magnitude of the velocity on an arbitrary plane in the flow. We have reached 1 second of run time here, and the solution has stopped. If we take a look at the drag monitor plot, we can see that the drag never really stabilizes. It continues to oscillate, and that is physically realistic. There's not too much to be told from the drag residuals graph without zooming in on any region on it. But the scalar plot tells us a little bit more. There's more stuff going on, as you would imagine, with a detached eddy simulation. However, the mesh resolution is really too large for a DES simulation to be meaningful. It would need to be a bit finer to really start capturing the eddies that get shed by this object. However, that will take very long to run, so we won't do it in an example case like this. But at least we've really demonstrated that it's fairly straightforward to run a detached eddy simulation. It's also quite straightforward to generate this type of mesh in the Star CCM Plus interface. Let's explore the other meshing options in Star CCM Plus. We were using the trim mesher with a prism layer mesher. We can also select tetrahedral meshing with a prism layer mesher. So let's regenerate a surface mesh and generate a volume mesh. We've used exactly the same size settings as we did with the previous mesh, but you'll see that it's a mesh with far more cells. It's now 452,000 cells. Let's update our mesh scene, because at the moment we've got it as a surface mesh representation. So let's apply the representation of the volume mesh. So now this is looking rather different. So it's now a tetrahedral mesh, and it's still got the prism layers as well. So this would be quite a good mesh to run for a simulation as well. We're not going to do this because we're not going to learn anything new from it.
Just looking at the calendar,
We also have the option of using polyhedral meshing. So let's back away again, drop the tetrahedral meshing and select polyhedral meshing. Once again with a prism layer mesher. We've already remeshed the surface, so let's generate the volume mesh. It's finished the polyhedral mesh generation, and as you can see we're back down to a cell count of around 132,000 cells. Let's apply the volume representation, and now it looks very different. So this is our polyhedral mesh. Polyhedral meshes just look nice. They look nice and smooth. You can easily imagine that they would work quite well. Well, we might as well run this model. So we can initialize the solution. It's repartitioning. We're running in parallel over 4 processor cores, so it has to repartition the mesh. In other words, move the mesh cells to the appropriate CPUs. Once it's finished with the repartitioning, we can start running it. So let's take a look at our residuals. We're running steady state again. In the interests of time, let's take a look at our coupled flow settings. We're running second order differencing on the convection schemes, and we should develop some oscillations on the forces as before. Our scalar scene is not updating, so we may need to apply the correct representation to it. Apply representation, volume mesh. There we go. So we've got a cut through the mesh, but you can see a interesting pattern as it cuts through the mesh cells. They appear as rather different sized cells, even though they are fairly uniform in cell size. Well, let's let it continue running. So we can watch the shear stress or the skin friction coefficient developing on the floor here. With these examples, we've only really scratched the surface of what you can do with these CFD products. They're immensely capable. The interfaces are very well developed. There's some good built-in help available. They're very, very mature products, and they've got an amazing number of models, physics models included. It is also possible to customize the physics model by doing some user coding. In Fluent, you write your user coding in C language. In StarCCM Plus, you follow a different approach. You have numerous options for developing user code for StarCCM Plus, including Python and Fortran. As before, we're seeing a solution developing here. Our drag monitor plot is oscillating as we expected it to do, and our residuals are very slowly starting to come down. The residuals on the turbulent kinetic energy equation are very reluctant to come down, but are now starting to come down a little bit as well. So as before, this is not an entirely physical flows situation to model with steady state, so do not expect a great convergence. At the conclusion of a simulation run like this, you will typically save your output file. In the case of StarCCM Plus, you write a file with the extension .sim. But you can also export the solution variables, and they can be exported to a number of different types of file format. This can be quite valuable. For example, you can export to Nsight. Nsight is a general purpose post-processing software package. It is also now in the Ansys stable of software, but you can write output from a variety of codes into a suitable format for Nsight. The reason why this would be useful to do is you'd be able to post-process and view the results also with Paraview, which is an open source post-processing program. In our previous example, we generated the geometry in a CAD program and then took it into either a CFD mesh generating program like Ansys Isom Cfd, or we brought the surface mesh from that CAD model into Siemens SimCenter StarCCM Plus to generate a mesh in this interface. But that's not the only way to do it. StarCCM Plus has some fairly sophisticated parametric CAD capabilities built in, so you can do geometry generation inside StarCCM Plus itself. And remember that I also mentioned earlier that Fluent's .msh mesh file format is quite widely supported, and it's entirely possible for us to import that existing volume mesh, which is generated with Isom Cfd, into StarCCM Plus. There we go. We've seen this geometry before. This is imported from the volume mesh generated with Isom Cfd, and if we create a new mesh scene, we're able to see that there's a very familiar looking mesh. This is not the mesh generated with StarCCM Plus, but this is the mesh rather generated using Isom Cfd, and it has arrived with all its boundaries, so we can set up boundary conditions as before and run it as before. So it's quite a useful capability if necessary in order to exchange meshes between different bits of CFD software. For what it's worth, there are also utilities to convert the .msh file format into a mesh format that can be read by OpenFOAM.
Righto, so that's it for today's demonstrations. I hope it's been of value to people. It's very superficial. I need to re-emphasize just what the tremendous capabilities are of these products. And a simple demonstration with a very simple test case like this cannot really do justice to them. But then again, if you do something more complex, the whole demonstration becomes a lot more tedious, and it's perhaps more difficult to identify the simple characteristics. So at this stage, I'd like to open up the discussion to anybody who would like to ask any questions about this.
Yeah, Charles, thank you very much. And maybe we need to remind the audience that there is still the book voucher competition for the best question of the session, of the lecture.
Yes. So don't all stick up your hands at once. Let me start then here with a question from my side. Have any of the people in the audience here actually used CFD software themselves? So you would all be novices then. Okay. Well, I hope then that this has given you an indication of what to expect of how this kind of software works. It's quite amazing the different philosophies that the different companies have used for developing their interfaces. Ultimately, they do more or less the same thing, but the approach used in developing interfaces is quite different. With Fluent, the interface is largely developed by or designed by people who actually use the software. So they follow a workflow approach. In other words, how would you logically proceed through getting hold of the geometry, preparing the geometry, preparing the mesh, setting up the solution, and then running the case. With StarCCM+, they've used a completely different approach, and the interface seems to be designed by a programmer in the sense that things are grouped together in the way that the programmer would do it in the software, rather than the user would like to see them being used together. So it takes some getting used to, especially if you regularly switch between the two types of programs. I've used a lot of different CFD products in my career, and actually neither of these two is at the top of my list of favorite interfaces. That prize goes to the interfaces developed by a company called, well, it used to be called CFDRC, and they got bought by the French company ESI, who developed a particularly logical set of interfaces for using all their products. But I guess much of that is personal preference. There was a time when using CFD software was regarded as being a great obstacle to wider adoption. And I think that's not been true for a very long time already. I think maybe 20 years or so. The software is quite easy to use. As you can see, the interfaces are very well developed. It's got good menus and there's good help and everything. So actually running the software is fairly trivial. It doesn't change the fact that you're dealing with a very complicated set of physics. You're dealing with, at its least, fluid dynamics, but most probably with a lot of other physics combined. So the emphasis is not so much on being able to run the software. The emphasis is understanding the physics and knowing what you're doing. Well, I think I'll stop it there. If nobody wants to get a free book from Francesco, we should stop the session then.
Okay, is there any more? Is there a first question? Yeah.
Okay, well, I think this time the audience has gone to sleep. I'll see you on Thursday afternoon at 2 o'clock then, and then we'll take a slower walk through OpenFOAM, because OpenFOAM is different. OpenFOAM is open source software. It comes with no interface to help you run the software. You can buy interfaces for it, but then that's no longer the open source or the free software approach, is it now? And there you actually need to deal barehanded with the input files and what they mean, and you've got to deal with rather startling lack of useful documentation. And you find that you have to find your assistants for answers, finding answers for running the software. You've got to find in other places, typically on the internet, but also having friends who know the software is also very valuable. So a slow walk through OpenFOAM is on the schedule for Thursday afternoon. I'll see you then.
Yeah, thank you very much, Charles. That was very interesting today, and I think OpenFOAM will also be very, very useful to our students, because that's what everybody will have immediately access to, since it's open source. Yeah.
Yes.
Okay, wonderful. Then just a quick reminder that we meet again at 2 o'clock this afternoon with the next lecture on machine learning by Professor Morton. And we are looking forward to see you there. Yeah. So Charles, again, thank you very much. And thank you to all the participants. And we will see you again in a couple of hours. Yeah. Thank you.
Goodbye, everyone. Cheers.
A good day and a good afternoon. Yeah. Thank you. Bye.